Hello, everyone. My name is Raphael Townshend. I'm one of the head TAs for this class. This week, Andrew's traveling, and my advisor is still dealing with medical issues, so I'm going to be giving today's lecture. You heard from my wonderful co-head TA, Anand, a couple weeks ago. And so today, we're going to be going over decision trees and various ensemble methods. So these might seem a bit like disparate topics at first, but really decision trees are sort of a classical example model class to use with various ensembling methods. We're going to get into a little bit why in a bit, but just to give you guys an overview of what the outline's going to be, we're first going to go over decision trees, then we're going to go over general ensembling methods, and then go specifically into bagging, random forests, and boosting. Okay, so let's get started. So first, let's cover some decision trees. Okay, so last week, Andrew was covering SVMs, which are sort of one of the classical linear models. And it sort of brought to a close a lot of our discussion of those linear models. And so today, we're going to be getting to decision trees, which is really one of our first examples of a nonlinear model. And so to motivate these guys, let me give you guys an example. Okay? So I'm Canadian. I really like to ski, so I'm going to motivate it using that. So pretend you have a classifier that, given a time and a location, tells you whether or not you can ski. So it's a binary classifier saying yes or no. And so you can imagine a graph like this. And on the x-axis, we're going to have time in months, so counting from the start. So starting at 1 for January to 12 for December. And then on the y-axis, we're going to use latitude in degrees, okay? And so for those of you who might have forgotten what latitude is, it's basically at positive 90 degrees, you're at the North Pole. At negative 90 degrees, you're at the South Pole. So positive 90, negative 90, 0 being the equator. And it's sort of your location along the north-south axis. Okay, so given this, if you might recall, the winter in the northern hemisphere generally happens in the early months of the year. So you might see that you can ski in these early months over here and have some positive data points. And then in the later months, like this, right? And then in the middle, you can't really ski. Versus in the southern hemisphere, it's basically flipped, where you can not ski in the early months. You can ski during the May, June, July, August time period. And then you cannot ski in the later months. And then the equator in general is just not great for skiing. There's a reason I don't live there. And so you just have a bunch of negatives here. Okay. And so when you look at a data set like this, you've sort of got these separate regions that you're looking at, right? And you sort of want to isolate out those regions of positive examples. If you had a linear classifier, you'd sort of be hard-pressed to come up with any sort of decision boundary that would separate this reasonably. Now, you could think, OK, maybe you have an SVM or something. You could come up with a kernel that could perhaps project this into a higher feature space that would make it linearly separable. But it turns out that with decision trees, you have a very natural way to do this. So to sort of make clear exactly what we want to do with decision trees is we want to sort of partition the space into individual regions. So we sort of want to isolate out these like positive examples, for example. And in general, this problem is fairly intractable, just coming up with the optimal regions. But how we do it with decision trees is we do it in this basically greedy, top-down, recursive manner. And this would be recursive partitioning. Okay? And so it's basically it's top down because we're starting with the overall region and we want to slowly partition it up. Okay? And then it's greedy because at each step we want to pick the best partition possible. Okay, so let's actually try and work out intuitively what a decision tree would do. Okay? So what we do is we start with the overall space. And the tree is basically going to play 20 questions with this space. Okay, so like for example, one question it might ask is, if we have the data coming in like this, is the latitude greater than 30 degrees? Okay? And that would involve sort of cutting the space like this, for example. Okay? and then we'd have a yes or a no. And so starting from like the most general space, now we have partitioned the overall space into two separate spaces using this question. Okay. And this is where the recursive part comes in now. Because now that you've sort of split this space into two, you can then sort of treat each individual space as a new problem to ask a new question about. And so for example, now that you've asked this latitude greater than 30 question, you could then ask something like month less than like March or something like that, right? And that would give you a yes or no. And what that works out to effectively is that now you've taken this upper space here and divided it up into these two separate regions like this. And so you could imagine how through asking these recursive questions over and over again, you could start splitting up the entire space into your individual regions like this. Okay. And so to make this a little bit more formal, what we're looking for is we're looking for sort of this split function. Okay, so you can sort of define a region. So you have a region, and let's call that region RP in this case for our parent. Okay, and we're looking for a split SP such that you have an SP. You can sort of write out this SP function as a function of j comma t. Okay, j is which feature number, and t is the threshold you're using. And so you can sort of write this out formally as sort of you're outputting a tuple, where on the one hand you have a set x, where you have the xj, the jth feature of x is less than the threshold, and you have x as element of RP, since we're only partitioning that parent region. And then the second set is literally the same thing, except it's just those that are greater than t. And so we can refer to each one of these as R1 and R2. Any questions so far? No? Okay. So we sort of defined now how we would sort of do this. We're trying to like greedily pick these picks that are partitioning our input space. And the splits are sort of defined by which feature you're looking at and the threshold that you're applying to that feature. A sort of a natural question to ask now is how do you choose these splits? Right? And so I sort of give this intuitive explanation that really what you're trying to do is you're trying to isolate out the space of positives and negatives in this case. And so what it's useful to define is a loss on a region. Okay, so define your loss L on R. Loss on R. And so for now, let's define our loss as something fairly obvious, is your misclassification loss. It's how many examples in your region you get wrong. And so assuming that you have given C classes total, you can define P hat C to be the proportion of examples in R that are of class C. Okay? And so now that we've got this definition where we have this P hat C of telling us the proportion of examples that we've got in that case, you can sort of define the loss of any region as loss, let's call it misclassification, is just 1 minus max over C of P hat C, okay? And so the reasoning behind this is basically you can say that for any region that you've subdivided, generally what you'll want to do is predict the most common class there, which is just the maximum P hat C, right? And so then all the remaining probability just gets thrown onto misclassification errors, okay? And so then once we do this, we want to basically pick, now that we have a loss defined, we want to pick a split that decreases the loss as much as possible. So you recall I've defined this region R parent, and then these two children regions, R1 and R2. And you basically want to reduce that loss as much as possible. So you want to basically minimize loss R parent minus loss of R1 plus loss of R2. And so this is sort of your parent loss and this is your children loss. Okay? And since you're picking, and basically what you're minimizing over in some case is this J comma T that we defined over here, since the split is really what is going to define our two children regions. Right? And what you'll notice is that the loss of the parent doesn't really matter in this case because that's already defined. So really all you're trying to do is minimize this negative sum of losses of your children. Okay? So let's move to this next board here. So I sort of defined this misclassification loss. Let's get a little bit into actually why misclassification loss isn't actually the right loss to use for this problem. So okay? And so for a simple example, let's pretend, so I've sort of drawn out a tree like this. Let's pretend that instead we have another setup here where we're coming into a decision node. And at this point, we have 900 positives and 100 negatives, okay? So this is sort of a misclassification loss of 100 in this case because you'd predict the most common class and end up with 100 misclassified examples. Right? And so this would be your region RP right now, right? And so then you can split it into these two other regions, right? Say R1 and R2. And say that what you've achieved now is you have this 700 positive, 100 negatives on this side versus 200 positives and 0 negatives on this side, okay? Now, this seems like a pretty good split since you're getting out some more examples. But what you can see is that if you just drew the same thing again, right, RP with 900, 100, split, split. And say in this case, instead, you got 400 positives over here, 100 negatives, and 500 positives. And 0 negatives. So most people would argue that this right decision boundary is better than the left one because you're basically isolating out even more positives in this case. However, if you're just looking at your misclassification loss, it turns out that on this left one here, let's call this R1 and R2 versus this right one, let's call this R1 prime, R2 prime. Okay? So your loss of R1 plus R2 on this left case is just 100 plus 0, right? So just 100. And then on the right side here, it's actually still just the same. And in fact, if you look at the original loss of your parent, it's also just 100, right? So you haven't really, according to this loss metric, changed anything at all. And so that sort of brings up one problem with the misclassification loss, is that it's not really sensitive enough, okay? So like, instead what we can do is we can define this cross-entropy loss, okay? So which we'll define as L cross. Let me just write this out here. And so really what you're doing is you're just summing over the classes, and it's the probability, the proportion of elements in that class times the log of the proportion in that class. And how you can think of this is, it's sort of this concept that we borrow from information theory, which is sort of like the number of bits you need to communicate to tell someone who already knows what the probabilities are, what class you're looking at. And so that sounds like a mouthful, but really you can sort of think of it intuitively as if someone already knows the probabilities, like say it's a 100% chance that it is of one class, then you don't need to communicate anything to tell them exactly which class it is, because it's obvious that it is that one class. Versus if you have like a fairly even split, then you need to communicate a lot more information to tell someone exactly what class you are in. Any questions so far? Yep. The R1, R2 for the parent class? For this case here? Yeah. So for that case there, so you see that, I'll try and reach up there, but so like say like RP was your start region, right? You could say it's the overall region, right? And then R1 would be all the points above this latitude 30 line, and R2 would be all the points below the latitude 30 line. Yeah. Yep. Mm-hmm. Yeah, so the question is, when you're trying to minimize this loss here, is it the same as maximizing the children loss? Let's see, of maximizing the children loss. And yeah, it turns out it doesn't really matter which way you put it. It's just basically you're trying to either minimize the loss of the children or maximize the gain in information, basically. Yeah, let's see. Yeah, you're right. That should actually be a max. You're right. Let me fix that really quick. Let's see. Because you start with your parent loss, and then you're subtracting out your children's loss. And so the amount left, let's see, the higher this loss is, yeah, so you really want to maximize this guy. Make sense, everyone? Thanks for that. Okay, so I've sort of given this like hand wavy. Oh, sure. What's up? So that would be log base 2. The question is, for the cross entropy loss, is it log base 2 or log base C? It's log base 2. Okay. Here, I can write that out. Yep. Or sorry, I didn't quite hear that. Okay. So the question is, what is the proportion that are correct versus incorrect for these two examples we've worked through here? And so, yeah, basically what we're starting with is we have 900, 100, 900 positives and 100 negatives, right? So you can imagine if you just stopped at this point, right, you would just classify everything as positive, right? And so you'd get 100 negatives incorrect if that makes sense, because this is 900 positives and 100 negatives. So if you just stopped here and just tried to classify given this whole region RP, you would end up getting 10% of your examples wrong, right? In this case, we're not talking about percentages, we're talking about absolute number of examples that we've gotten wrong. But you can also definitely talk in terms of percentages instead. And then down here, once you've split it, right, now you've got these two subregions, right? And on this left one here, you still have more positives than negatives, right? So you're still going to classify positive in this leaf, right? And you're still going to classify positive in this leaf too, because they're both majority class, or the positives are still the majority class there. And in this case, since you have 0 negatives, you're not going to make any errors in your classification. Versus in this case here, you're still going to make 100 errors. And so what I'm saying is that at this level, so if we just look above this line at RP, right, you're making 100 mistakes. And then below this line, you're still making 100 mistakes. So what I'm saying is that the loss in this case is not very informative. So this p hat, okay, I'm being a little bit loose with the notation here, but the p hat in this case is a proportion, okay? But you can also easily, basically it's like whether you're normalizing the whole thing or not. Yeah. Okay. So I've sort of given this a bit hand-wavy explanation as to why misclassification loss versus cross-entropy loss might be better or worse. We can actually get a fairly good intuition for why this is the case by looking at it from a sort of geometric perspective. So pretend now that you have this plot, okay? And what you're plotting here is, pretend you have a binary classification problem, okay? So you have just, is it positive class or negative class, okay? And so you can sort of represent, say, p hat as like the proportion of positives in your set, okay? And what you've got plotted up here is your loss. Okay, for cross-entropy loss, what your curve is going to end up looking like is it's going to end up looking like this strictly concave curve like this, okay? And what you can do is you can sort of look at where your children versus your parents would fall on this curve. So say that you have 2 children, okay? You have one up here, so let's call this LR1. And you have one down here, LR2, okay? And say that you have an equal number of examples in both R1 and R2, so they're equally weighted. If you take, when you're looking at the overall loss between the two, right, that's really just the average of the two. So you can draw a line between these two, and the midpoint turns out to be the average of your 2 losses. So this is LR1 plus LR2 divided by 2. That's what this guy is. Okay? And what you can notice is that, in fact, the loss of the parent node is actually just this point projected upwards here. So this would be your LR parent. And this difference right here, this difference, is sort of your change in loss. Does this make sense? Any questions? Okay, so we have this, just to recap, okay, so we have, say we have 2 children regions, right? And they have different probabilities of positive examples occurring, right? They sort of would fall, one would fall on this point on the curve, and say the other one falls on this point on the curve. Then the average of the 2 losses sort of falls on the midpoint between these 2 original losses. And if you look at the parent, it's really just halfway between on the x-axis, and you can project upwards for that as well, and you end up with the loss of our parent. What's up?
I don't really understand what point on the curve is and why with the loss of the parent on the same curve as the loss of the children.
Okay, so what we're looking at here is we're looking at the cross-entropy loss. So you've got this function here, this L cross-entropy, right? And that's in terms of p hat c's, right? And in this case, here we're just assuming that we have 2 classes, okay? And so what we're doing is we're just modifying the p hat c. we're changing that on the x-axis, and then we're looking at what the response of the overall loss function is on the y-axis. And so what I just did here is for any, this curve just represents for any p hat c what the cross-entropy loss would look like, okay? And so we can come back to this, for example, right? And if we look at this parent here, right, this guy has a 10%, right? It's sort of like p hat for this guy is 0.1. It's 10% basically, or I guess, no, in this case it would be 0.9, sorry. And then versus here, in these two cases, right, your p hat in this case is 1, since you've got them all right? And then in this case, it's 0.8, right? And so you can sort of see, since these are equal, there's the same number of examples in both of these. The p hat of the parent is just the average of the p hats of the children, okay? And so that's how we can sort of take this LR parent. This LR parent is just halfway. If we projected this down, right? Let me just erase this little bit here. If we projected this down like this, we'd see that this point here is the midpoint. Okay? And, but then when you're actually averaging the two losses after you've done the split, then you can basically you're just taking the average loss, right? You're just summing LR1 plus LR2, and if you're taking the average, then you're dividing by 2. And what you can do is you can just draw the line and take the midpoint of this line instead. Yep. Yeah.
If you had like, I don't know, 300 on this side, 100 on the other side, then you can do like a weighted average, and then for RP, you plot from the same weighted average point on Ensemble, right?
Yeah, exactly. So yeah, really it's a good point. The question was, if you have an uneven split, what would that look like on this curve, right? And so at this point, I've been making the math easy by just saying there's an even split, but really, if there was a slightly uneven split, the average would just be any point along this line that you've drawn. And as you can see, the whole thing is strictly concave, so any point along that line is going to lie below the original loss curve for the parent. So you're basically, as long as you're not picking the exact same points on the probability curve and not making any gain at all in your split, you're going to gain some amount of information through this split. Okay. Now, this was the cross-entropy loss, right? If instead we look at the misclassification loss over here, let's draw this one instead. What we can see in this case, if you draw it, is that it's in fact really this pyramid kind of shape, where it's just linear and then flips over once you start classifying the other side. And if you did the same argument here, where you had LR1 and LR2, and then you drew a line between them, right? That's basically just still the loss curve. And so in this case, like your midpoint would be the same point as your parent. So your loss of our parent in this case would equal your loss of R1 plus loss of R2 divided by 2. Right? And so in this case, even though according to the cross-entropy formulation, you do have a gain in information, and intuitively we do see a gain in information over here. For the misclassification loss, since it's not very sensitive, if you end up with points on the same side of the curve, then you actually don't see any sort of information gain based on this kind of representation. And so there's actually a couple. I presented the cross-entropy loss here. There's also the Gini loss, which is another one, which people just write out as the sum over your classes p hat c times 1 minus p hat c. Okay? And it turns out that this curve also looks very similar to this original cross-entropy curve. And what you'll see is that actually most curves that are successfully used for decision splits look basically like this strictly concave function. Okay, so that sort of covers a lot of the criteria we use for splits. Let's look at some extensions for decision trees. Actually, I'm going to keep this guy. Okay, so far I've been talking about decision trees for classification. You could also imagine having decision trees for regression, and people generally call these regression trees, okay? And so taking the ski example again, let's pretend that instead of now predicting whether or not you can ski, you're predicting the amount of snowfall you would expect in that area around that time. And so like I'm just gonna say it's like inches of snowfall, I guess, or something per like day or something, and just like maybe you have some values up here, some high values because it's winter over there, it's mostly zeros over here because you're summer, and then you have some more high values over here, and then you have zeros along the equator again. Zeros, southern hemisphere over our winter. And then more zeros like this. And you can sort of see how you would do just the exact same thing. You still want to isolate out regions and sort of increase like the purity of those regions. So you could still create like your trees like this, right? And split out like this, for example. And what you do when you get to one of your leaves is instead of just predicting a majority class, what you can do is predict the mean of the values left. So you're predict y hat, where, well, for Rm, so pretend you have a region Rm, you're predicting y hat of m, which is the sum of all the indices in Rm, yi minus y hat m. And you want the squared loss, and then you can sort of, I guess in this case, you want to normalize by the overall cardinality of Rm, or how many points you have in Rm. And so in this case, basically all you've done is you've switched your loss function, no, sorry, that's wrong. This is actually, I got a little bit ahead of myself. This is actually just, the mean value would just be this in this case, right? It's just you're summing all the values within your region, so in this case 7, 9, 8, 10, and then just taking the average of that. But so then what you do, what I was starting to write out there was actually really the loss that you would use in this case, right? Which is your squared loss, okay? So like we'll just call that L squared, which in this case would be equal to yi minus y hat m squared over Rm. And that's what I started to write over there. But in this case, right, you have your mean prediction, and then your loss in this case is how far off your mean prediction is from the overall predictions in this case. Yep?
So in terms of like the actual process for finding these boundaries,
Yep.
we take the gradient with respect to our parameters of these loss functions and set it to 0, or do we try to iterate through different possible boundaries and select the best one?
So that's a really good question. The question was, how do you actually search for these splits? How do you actually solve the optimization problem of finding these splits? And it turns out that you can actually basically brute force it very efficiently. I'm going to get into sort of the details of how you do that shortly, but it turns out that you can just go through everything fairly quickly. I'll get into that. I think that's in a couple sections from now. Any other questions? No? Okay. So this is for regression trees, right? It turns out that another useful extension that you don't really get for other learning algorithms is that you can also deal with categorical variables fairly easily. And basically, for this case, you could imagine that instead of having your latitude in degrees, you could just have 3 categories, right? You could have something like, this is the northern hemisphere, this is the equator, and this is the southern hemisphere, okay? And then you could ask questions instead of the sort, like that initial question we had before where it was latitude greater than 30, your question could instead be I guess this would be, is location in northern hemisphere, right? And so you could have basically any sort of subset, you could ask a question about any sort of subset of the categories you're looking at. Right, so in this case, northern, this question would still split out this top part from these bottom pieces here. One thing to be careful about, though, is that if you have Q categories, then you have, you basically are considering every single possible subset of these categories. So that's 2 to the Q possible splits. And so in general, you don't want to deal with too many categories because this will become quickly intractable to look through that many possible examples. It turns out that in certain very specific cases, you can still deal with a lot of categories. One such case is for binary classification, where then you can just, the math is a little bit complicated for this one, but you can basically sort your categories by how many positive examples are in each category, and then just take that as like a sorted order and then search through that linearly. And it turns out that that yields you an optimal solution. Okay. So decision trees, we can use them for regression. We can also use them for categorical variables. One thing that I've not gotten into is that you can imagine that in the limit, if you grew your tree without ever stopping, you could end up just having a separate region for every single data point that you have. And so that's really, you could consider that probably overfitting if you ran it all the way to that completion, right? So you can sort of see that decision trees are fairly high variance models. And so one thing that we're interested in doing is regularizing these high variance models. And generally how people have solved this problem is through a number of heuristics, okay? So one such heuristic is that if you hit a certain minimum leaf size, you stop splitting that leaf, okay? So for example, in this case, if you've hit like you only have 4 examples left in this leaf, then you just stop. Another one is you can enforce a maximum depth. And sort of a related one in this case is a max number of nodes. And then a fourth, very tempting one, I've got to say, to use is you say a minimum decrease in loss, right? Right? And I say this one's tempting because it's generally not actually a good idea to use this minimum decrease in loss one. And you can think about that by thinking that if you have any sort of higher order interactions between your variables, you might have to ask one question that is not very optimal or doesn't give you that much of an increase in loss, and then your follow-up question combined with that first question might give you a much better increase. And you can sort of see that in this case, where our initial latitude question doesn't really give us that much of a gain. We sort of split some positive and negatives, but the combination of the latitude question plus the time question really nails down what we want. And if we were looking at it purely from the minimum decrease in loss perspective, we might stop too early and miss that entirely. And so a better way to do this kind of loss decrease is instead you grow out your full tree and then you prune it backwards instead. So you grow out the whole thing and then you check which nodes to prune out. Pruning. And how you generally do this is you have a validation set that you use this with, and you evaluate what your misclassification error is on your validation set for each example that you might remove, or each leaf that you might remove. So you would use misclassification in this case. With a validation set. Any questions? Yep. The minimum decrease in loss? So, yeah, of course. So you'll recall that before I was talking about sort of this RP, this loss of R parent versus loss of R1 plus loss of R2, right? So when I had written out a maximization, basically. To be clear, the question is, can you explain a little bit more clearly what this minimum decrease in loss means? And so you have your loss of R1 and R2 versus your loss of R parent, right? So the split, before the split, right, you have your loss before split, you have loss of R parent. And then after split, you have loss of R1 plus loss of R2. Right? And if this decrease between your loss of R parent to your loss of your children is not great enough, you might be tempted to say, okay, that question didn't really gain us anything, and so therefore we will not actually use that question. But what I'm saying is that sometimes you have to ask multiple questions, right? You have to ask sort of suboptimal questions first to get to the really good questions, especially if you have sort of interaction between your variables, if there's some amount of correlation between your variables. Okay. So we talked about regularization. I said that we would get to runtime. Let's just go up here again. So let's cover that really quickly. Okay, so it'll be useful to just define a couple of numbers at this point. So say you have n examples. You have f features. And finally, you have d, say the depth of your tree is d, okay? All right, so you have n examples that you trained on. Each has f features, and your resulting tree has depth d. So at test time, your runtime is basically just your depth d, right? It's just O of d, right? Which is your depth. And typically, though in not all cases, d is sort of is less than the log of your number of examples. And you can sort of think about this as if you have a fairly balanced tree, right, you'll end up sort of evenly splitting out all the examples and sort of recursively like doing these binary splits, and so you'll be splitting it at the log of that n. Okay, so at test time, you've generally got it pretty quick. At train time, you have each point. So if you return back to this example, you'll see that each point, right, once you've done a split, only belongs to the left or right of that split afterwards. Right? So it's sort of like this point right here, once you've split here, will only ever be part of this region. Will never be considered on the other side, on the right-hand side of that split. Right? So if your tree is of depth d, each point is part of OD nodes. Okay? And then at each node, you can actually work out that the cost of evaluating that point at train time is actually just proportional to the number of features, f. And I won't get too much into the details of why this is, but you could consider that if you're doing binary features, for example, where each feature is just yes or no of some sort, then you only have to consider, if you have f features total, you only have to consider f possible splits. And so that's why the cost in that case would be f. And then if it was instead a quantitative feature, I mentioned briefly that you could sort the overall features and then scan through them linearly. And that also ends up being asymptotically O of f to do that. Okay, so each point is at most O of d nodes, and then the cost of a point at each node is O of f, and you have n points total. So the total cost is really just O of n f d, like this. And it turns out that this is actually surprisingly fast, especially if you consider that n times f is just the size of your original design matrix, right, or your data matrix, right? Your data matrix is of size n times f, right? And then your runtime is going through the data matrix at most depth times. And since depth is log of n, that turns out to be, or generally bounded by log of n, you have generally fairly fast train time as well. Any questions about runtime? Okay, so I've been talking a lot about the good sides of decision trees, right? They seem pretty nice so far. However, there are a number of downsides too. And one big one is that it doesn't have additive structure to it. And so let me explain a little bit what that means. Okay, so let's say now we have an example where you have just two features again, so x1 and x2. And you could say you define a line, okay, just running through the middle, defined by x1 equals x2. And all the points above this line are positive. And all the points below it are negative. Now, if you had a simple linear model like logistic regression, it would have no issue with this kind of setup. But for a decision tree, basically, you'd have to ask a lot of questions to even somewhat approximate this line. Like what you could try is you could say, okay, let's split it this way, and maybe we can do a split this way, and then another split here, maybe something like this, and basically something like that, right? And even here, you've asked a lot of questions, and you've only gotten a very rough approximation of the actual line that you've drawn in this case. And so decision trees do have a lot of issues with these kind of structures where the features are interacting additively with one another. Okay, so to recap so far, since we've covered a number of different things about decision trees, there's a number of pluses and minuses to decision trees. Okay, so on the plus side, they're actually, I think this is an important point, is that they're actually pretty easy to explain, right? If you're explaining what a decision tree is to like a non-technical person, it's fairly obvious. You're like, okay, you have this tree, you're just playing 20 questions with your data and letting it come up with one question at a time. They're also interpretable. You can just draw out the tree, especially for shorter trees, to see exactly what it's doing. It can deal with categorical variables. And it's generally pretty fast. Right? However, on the negative side, one that I alluded to was that they're fairly high variance models, and so are oftentimes prone to overfitting your data. They're bad at additive structure. And then finally, they have, in large part because of these first two, they generally have fairly low predictive accuracy. I know what you guys are thinking. I just spent all this time talking about decision trees, and then I tell you guys they actually sort of suck. So why did I actually cover decision trees? And the answer is that, in fact, you can make decision trees a lot better through ensembling. And a lot of the methods, for example, the leading methods in Kaggle these days are actually built on ensembles of decision trees. And they really provide an ideal sort of model framework to look at through which we can examine a lot of these different ensembling methods. Any questions about decision trees before I move on? Yeah? I don't think that's strictly, okay, so the question is, for the cross-entropy loss, does the log need to be base 2? And the answer is, I'm pretty sure that is not very relevant in this case. I'm not 100% sure about that, but I'm pretty sure that the base of the log doesn't make sense. Cross-entropy loss actually initially came out of like information theory, where you have like computer bits and you're transmitting bits. And so it's useful to think in terms of bits of information that you can transmit, which is why it came up as log base 2 in the initial formulation. Okay, so now let's talk about ensembling. Okay, so why does ensembling help? At some level, you can sort of think back to your basic statistics. So say you have xi's, which are random variables. I'll sometimes write this as just RV, that are independent, identically distributed. And so probably a lot of you are familiar with this already, but you can call this IID. Okay? Now say that your variance of one of these variables is sigma squared. Then what you can show is that the variance of the mean of many of these variables, so of many of these random variables, or written alternatively, 1 over n sum over i's of xi, is equal to sigma squared over n. And so each independent variable you factor in is decreasing the variance of your model. Right? And so the thought is that if you can factor in a number of independent sources, you can slowly decrease your variance. Okay, so I've sort of, though this is a little bit simplistic of a way of looking at this, because really all these different things you're factoring together have some amount of correlation with each other. And so this independence assumption is oftentimes not correct. So if instead you drop the independence assumption, so now your variables are just ID, right? Okay, and say we can characterize what the correlation between any two xi's is, and we can write that down as rho. So, xi's then you can actually write out the variance of your mean as rho sigma squared plus 1 minus rho over m, or no, n, sigma squared. Okay, and so you can sort of see that if they're fully correlated, then this term will drop to 0, and you'll just have sigma squared again, because adding a bunch of fully correlated variables is just going to give you the original variable's variance. Versus if they're completely decorrelated, then this term drops to 0, and you just end up with sigma squared over n, which gives you the initial independent, identically distributed equation. And so in this case, really what you want to do, the name of the game is you want to have as many different models that you're factoring as possible to increase this n, which drives this term down. And then on the other hand, you also want to make sure those models are as decorrelated as possible so that your rho goes down and this first term goes down as well. Okay? And so this gives rise to a number of different ways to ensemble. And one way you could think about doing this is you just use different algorithms. Right? This is actually what a lot of people in Kaggle, for example, will do, is they'll just take a neural network, a random forest, an SVM, average them all together, and generally that actually works pretty well, but then you sort of have to spend your time implementing all these separate algorithms, which is oftentimes not the most efficient use of your time. Another one that people would like to do is just use different training sets. Okay? And again, in this case, like, you probably spend a lot of effort collecting your initial training set. You don't want your machine learning person to just come and recommend to you that just go collect a whole second training set or something like that to improve your performance. Like, that's generally not the most helpful recommendation. Okay? And so then what we're going to cover now are these two other methods that we use to do ensembling. And one of them is called bagging, which is sort of trying to approximate having different training sets. I'll get into that quickly. And then you also have boosting. And just so that you guys will have a little bit of context, we're going to be using decision trees to talk a lot about these models. And so bagging, you might have heard of random forest. That's a variant of bagging for decision trees. And then for boosting, you might have heard of things like AdaBoost or XGBoost, which are variants of boosting for decision trees. Okay, so that sort of covers at a high level what we'd want to do. These first two are very nice because they sort of would give us a much more like independently correlated or less correlated variables. But generally we end up doing these latter two because we don't want to collect new training sets or train entirely new algorithms. Okay, so let's cover bagging first. Okay, so bagging really stands for this thing. It's called Bootstrap Aggregation. Okay. And so first, let's just break down this term. So bootstrap, what that is it's typically this method used in statistics to measure the uncertainty of your estimate. Okay. And so what is useful to define in this case for when you're talking about bagging is you can say that you have a true population P, okay? And your training set S is sampled from P, right? So you just start drawing a bunch of examples from P, and that's what forms your training set at some level. And so ideally, like for example, this different training sets approach, what you do is you just draw S1, S2, S3, S4, and then train your model in each one of those separately. Unfortunately, you generally don't have the time to do that. And so what bootstrapping does is you assume basically that your population is your training sample. Okay? So you assume that your population is your training sample. And so now that you have this S is approximating your P, then you can draw new samples from your population by just drawing samples from S instead. Okay? So you have bootstrap samples, is what they're called. Z sampled from S. And so how that works is you basically just take your training sample, okay, say it's of like cardinality n or something, and you just sample n times from S, and this is important, you do it with replacement, because they're pretending that this is a population, and so doing it with replacement sort of makes that assumption hold, that you're sampling from it as a population. Okay, so that's bootstrapping. So you generate all these different bootstrap samples Z from your training set. And what you can do is you can take your model and train it on all these separate bootstrap samples. And then you can sort of look at the variability and the predictions that your model ends up making based on these different bootstrap samples. And that gives you sort of a measure of uncertainty. I'm not going to go into too much detail on that because that's not actually what we're going to use bootstrapping for. What we want to use bootstrapping for is we want to aggregate, basically, bootstrap samples. And so at a very high level, what that means is we're going to take a bunch of bootstrap samples, train separate models on each, and then average their outputs. Okay? So let's make that a little bit more formal. So you have bootstrap samples. Z1 through Zm, say. Okay, capital M. That's just say how many bootstrap samples you're going to take. Okay, you train a model, Gm, okay, on Zm. Okay? And then all you're doing is you're just defining this new sort of meta model. I'm not putting a subscript on this one to show that it's the meta model, G of M, which is just the sum of your predictions of your individual models divided by the total number of models you have. Right? So And this is just writing out what I was sort of talking about right up there for bagging. You're taking these bootstrap samples, and then you're training separate models, and then you're just aggregating them all together to get this bagging approach. And so if we just do a little bit of analysis from the bias variance perspective on this, we can sort of see why this kind of thing might work. And so you recall we have this equation up here, right? The variance of the mean is rho sigma squared plus 1 minus rho over n of sigma squared. So let me just write that out here to be clear. And in this case, our m is actually really just the number of bootstrap samples. So we'll just use big M in this case. And what you're doing is by taking these bootstrap samples, you're sort of decorrelating the models you're training. You're bootstrapping is driving down rho, okay? And so by driving this down, you're sort of making this term get smaller and smaller. And then your question might be, okay, what about this term here? And it turns out that basically you can take as many bootstrap samples as you want, and that'll slowly drive down, it increases m and drive down this second term. And it turns out that one nice thing about bootstrapping is that increasing the number of bootstrap models you're training doesn't actually cause you to overfit any more than you were beforehand. Because all you're doing is you're driving down this term here. So more m is just less variance, right? All you're doing is driving down the second term as much as possible when you're getting more and more bootstrap samples. So it generally only improves performance. And so generally what people will do is they'll sample more and more models until they see that their error stops going down, because that means they basically eliminated this term over here. So this seems kind of nice, right? You're decreasing the variance. Where's the trade-off coming in? Oh, there's a question. Yeah, there's definitely a bound, right? Because I'm not going to define one formally right now. Oh, the question is, can you define a bound on how much you decrease rho by? Yeah, so there's definitely a lower bound, a lower bound on how far you can decrease rho. Basically, it comes down to your bootstrap samples are still fairly highly correlated with one another, right? Because you're still just drawing it from the same sample set S. Really, your Z is going to end up containing about each Z is going to contain about 2/3 of S. And so your Z's are still going to be fairly highly correlated with each other. And though I don't have a formal equation to write down as to exactly how much that decreases rho by, or how much that bounds rho by, you can sort of see intuitively that there is a bound there, and that you can't just magically decrease rho all the way down to 0 and achieve 0 variance. All right. So I was saying that you decrease variance. This seems very nice. One issue that comes up with bootstrapping is that, in fact, you're actually slightly increasing the bias of your models when you're doing this. And the reasoning for that is because of this subsampling that I was talking about here. Each one of your Z's is now about 2/3 of the original S. So you're training on less data, and so your models are becoming slightly less complex, and so that increases your bias in this case. Yes?
Could you just re-explain the analogy between a random variable and an algorithm?
Yeah, for sure. So the question is, can you explain the difference between a random variable and an algorithm in this case, right? And so you can sort of, at a very high level, you can think of an algorithm as a classifier, as a function that's taking in some data and making a prediction, right? And if you sort of see that whole setup as sort of like the algorithm as giving some sort of output in a probabilistic perspective, you can sort of see the algorithm as like a random variable in this case. Sort of like you're basically considering sort of the space of possible predictions that your algorithm can make. And that you can sort of see as a distribution of possible predictions, and that you can approximate that as a random variable. I mean, it is a random variable at some level, because it's sort of like based on what training sample you end up with, your predictions of your output model are going to change. And so since you're sampling sort of these random samples from your population set, you can consider your algorithm as sort of based on that random sample, and therefore a random variable itself. Okay, so yeah, your bias is slightly increased because of random subsampling. But generally, the decrease in variance that you get from doing this is much larger than the slight increase in bias you get from doing this randomized subsampling. So in a lot of cases, bagging is quite nice. Okay? Okay, so I've talked a bit about bagging. Let's talk about decision trees plus bagging now. Okay, so you recall that decision trees are high variance, low bias. Okay? And this right here sort of explains why they're a pretty good fit for bagging. Okay? Because bagging, what you're doing is you're decreasing the variance of your models for a slight increase in bias. And since most of your error from your decision trees is coming from the high variance side of things, by sort of driving down that variance, you get a lot more benefit than for a model that would be on the reverse, high bias and low variance. Right? So this makes this like an ideal fit for bagging. Okay, so now this is sort of decision trees plus bagging. I said that random forests are sort of a version of decision trees plus bagging. And so what I've described here is actually almost random forests at this point. The one key point we're still missing is that random forests actually introduce even more randomization into each individual decision tree. And the idea behind that is that, as I had that question from before, is this row, you can only drive it down so far through just pure bootstrapping. But if you can further decorrelate your different random variables, then you can drive down that variance even further. Okay? And so the idea there is that basically at each split for random forests, you consider only a fraction of your total features, right? So it's sort of like for that ski example, maybe like for the first split, I only let it look at latitude. And then for the second split, I only let it look at the time of the year. And so this might seem a little bit unintuitive at first, but you can sort of get the intuition through two ways. One is that you're decreasing rho. And then the other one is you can think that, say you have a classification example where you have one very strong predictor that gets you very good performance on its own. And regardless of what bootstrap sample you select, your model is probably going to use that predictor as its first split. That's going to cause all your models to be very highly correlated right at that first split, for example. And by instead forcing it to sample from different features instead, that's going to increase or decrease the correlation between your models. And so it's all about decorrelating your models in this case. And that sort of brings to a close a lot of our discussion of bagging. Are there any questions regarding bagging? Okay. Now I've covered bagging, let's get a little bit into boosting. And I'll make this quick, but basically, whereas bagging, we sort of saw in the intuition that we were decreasing variance, boosting is sort of actually more of the opposite, where you're decreasing the bias of your models, okay? So, and also, it's basically more additive in how it's doing things. So versus, you'll recall that for bagging, you were taking the average of a number of variables. In boosting, what happens is you train one model, and then you add that prediction into your ensemble. And then when you train a new model, you just add that in as a prediction. And so that's a little bit hand-wavy right now, so let me actually make that clear through an example. So say you have a data set, again, x1, x2, x2, and you have some data points, maybe some, let's actually just call it pluses and minuses. Say you have some more pluses here, and then maybe a couple minuses, and then some pluses here. Okay? And what you say you're training size 1 decision trees, so decision stumps is what we call them. It's you only get to ask one question at a time. And the reasoning behind this, just really quickly, is that because you're decreasing bias by restricting your trees to be only depth 1, you basically are increasing their amount of bias and decreasing their amount of variance, which makes them a better fit for boosting kind of methods. And say that you come up with a decision boundary, okay, say this one here. Okay? And what you're going to do is on this side you predict positive, right? And on this side you predict negative. This is like a reasonable line that you could draw here, but it's not perfect, right? You've made some mistakes. And in fact, what you can do is you can sort of identify these mistakes. So if we draw this in red, right, you've made these guys as mistakes. And what boosting does is basically it increases the weights of the mistakes you've made. And then for the next decision stump that you train, it's now trained on this modified set, which we can, let's just draw it over here. That's 1. And so now these positives, I'll just draw them much bigger. You know, you've got big positives here and some small negatives and some small positives, some big negatives here. And so now your model, to try and get these right, might pick a decision boundary like this, right? And this is also basically recursive in that each step, right, you're going to be reweighting each of the examples based on how many of your previous ones have gotten it wrong or right in the past. And so basically what you're doing is you can sort of weight each one of these classifiers. You can determine for classifier GM a weight alpha M, which is proportional to how many examples you got wrong or right. So a better classifier, you want to give it more weight, and a bad classifier, you want to give it less weight. Proportional. And I think that the exact equation used in AdaBoost, for example, is just log of 1 minus the error of your mth model divided by basically log odds. Okay? And then your total classifier is just f of x, or let's just call it g of x again. G of x is just the sum over m of alpha m g of m. Okay? And then each g of m is trained on a weighted, on a reweighted actually, reweighted training set. And so I've glossed over a lot of the details here in interest of time, but the specifics of an algorithm like this will be in the lecture notes. And this algorithm is actually known as AdaBoost. And basically, through similar techniques, you can derive algorithms such as XGBoost or gradient boosting machines that also allow you to basically reweight the examples you're getting right or wrong in this sort of dynamic fashion and slowly adding them in this additive fashion to your composite model. And that about finishes it for today. Thanks for coming. Yeah, have a great rest of your week.